Dear friends, students and learners, welcome to this session. I am Shashank Shrivastava from School of Engineering and Technology in Indira Gandhi National Open University, and we were discussing about the unit of plastics and reinforced plastics. So moving ahead, today in this session we are discussing the composite materials. So what are the composite materials? Any two different materials which neither react chemically nor dissolve in each other, and if they combine together then they form composite materials. And out of these two constituents which form the composite, one acts as a binder, meaning it will hold the things together, and the other one may be in micro or macro form. Main purpose of making this composite is that we want certain properties, certain better properties which are not exhibited by the individual material out of the two which combine together to form the composite. And most common one which we may have heard about, you all also must have heard about or seen, is the reinforced cement concrete, of which we make slabs also in our building construction. Hard particles and softer metal matrix make composite materials of exceptionally good strength required for metal cutting tools. So this composite can also be utilized for metal cutting tools, and in that the condition is this, that hard particles and softer metal matrix are required. Then we have the fiber reinforced plastics also. You must have heard FRPs, short form, very famous FRP. So you may have known about it. We use in the cooling tower fan blades also, and other purposes also. So it's very common, and it is made by putting strong fibers in a matrix of weaker plastic material form, and this is very important in all kinds of engineering practice. Carbon and glass fibers are the most commonly used one, where we use them as reinforcement in a variety of plastics. So the fibers which we talked about in fiber reinforced plastic, the most common are the carbon and the glass ones. The ideal material for structural applications need to be strong, tough and light. So whenever we want certain material for structural application, then basic properties that we need are what? Strength we need, then we need toughness, so that it is not that brittle and it doesn't break very early, and then it has to be light also, because too heavy things are difficult to handle. And what we see actually in which of the materials these properties are there, like in metals, the strength is there, the toughness is there, but it is not light. In case of plastics, it is light but it doesn't have strength and toughness. So then we have to work out a combination of these two so that we can get the strength, toughness and lightness all together. So just an overview of the historical use of the composites, what has been done in the past. So Egyptians during the days of pharaohs used bricks reinforced with chopped straw. So it was a kind of composite. Plant fibers were used for strengthening potteries in South America and India also. And Eskimos strengthened ice by using moss. Moss is a kind of plant material as a reinforcing constituent. So when we talk of composites and the fibers, so first of all we start with the glass type of fibers, what all its properties are and where they are used. So the glass fibers have high strength than the bulk glass, and they actually can be conveniently drawn from this bulk glass which we use, but they cannot be used in structure due to their high brittleness. The glass is quite brittle, so they cannot be used in that form. So what we can do then, the softer plastic material has good adhesion with brittle and very thin fibers of glass, and protects them from atmospheric attacks by surrounding them in a composite. So we will do, we will mix, whether if this is brittle also, this glass, we will mix it with softer plastic matrix, and then it will not break because it will be protected from atmospheric attacks by the surrounding of the plastic layer which is soft. Glass reinforced plastic, this is called the GRP in short form, and it can be easily molded into shapes of varied geometry. So this GRP can be molded into different geometric forms. This is very useful. Glass fibers will be laid in a mold along longitudinal direction, and they can be molded in this way by pouring molten plastic or even by brushing the plastic on framework formed by fibers of glass. So there are two ways. One can be that the glass is put in a vessel and then in that mold, and then this plastic is poured into it in liquid form, or the other way around, that the plastic can be brushed upon with this glass fiber. And some examples of these, like the kitchen sinks and the bathtubs and motor car body parts, swimming pools, even aeroplane bodies are nowadays made of GRP, glass reinforced plastics. So after the glass fibers, now we discuss about the carbon fibers and some other types of fibers also. So carbon fibers are best known for their electrical resistance, property and fragility, and they have a strong covalent bond between two carbon atoms, and this makes the carbon fibers very strong. These fibers were found to develop high strength adhesive bonding with epoxy resin, and that resulted into fiber reinforced plastics, which we have discussed earlier, and this was as strong as steel but lighter than aluminum. So strength is as good as steel, but it is lighter than aluminum. So its application is very widespread because of this property. We must have heard about carbon composites. So this is the thing here. The carbon combines with epoxy adhesive and forms a very good material of high strength and light weight also. Large scale commercial production of these carbon fiber reinforced plastic already began in the 60s, and actually they are used in the aeroplanes also. Then we have got apart from this carbon fiber, there is the boron fiber also, and this seems to provide strength higher than the carbon fiber, but it is costlier. So cost also is a factor. That's why carbon is more prevalent than the boron one. Other fibers are there that have been tried, and these are of the silicon carbide and several other ceramics. However, the glass and carbon fibers by far are the major reinforcing fibers in plastic matrix. So now we move on to some technical terminologies. This one is called the figure of merit. So what it is the ratio of modulus of elasticity to density, that is E by rho, as given by the formula E by rho, and it is known as the figure of merit of a material. So aluminium, magnesium, wood and glass have these ratios which are very close to that of steel. So E by rho is for aluminium and magnesium, all these things are very close to steel. Plastics have ratio which is much smaller, that means the strength is lesser, but when these glass fibers are mixed with it, they make a reinforced type of material, then it becomes good. Materials that have their figure of merit even higher than those of iron, steel, aluminium and wood actually are very brittle, and so they are not fit for use in structures. Then we had discussed about the boron fibers and beryllium, carbon, etc. These are examples of material, those have very high modulus of elasticity. So E by rho will be good then. So now we will try to know about the modulus of elasticity of a composite. We have learnt what is a composite. Now what is the modulus of elasticity of a composite? So composite is basically made of two constituents. One is the matrix, called the matrix, and is represented by the capital M, and the other one is the fiber, represented by the capital F. And suppose that the length of both these is 1, that is unity. We are just assuming that thing. Then say that the cross-sectional area is respectively AM and AF. That means AM is the cross-sectional area of the matrix and AF is the cross-sectional area of the fiber. Then what will be the volume of the matrix? It will be again AM, because we have taken the length to be unity, and that of the fiber will also be AF. And suppose that the total force that acts axially on this particular composite, suppose it is somewhat a cylindrical type, the composite, and the cylinder is being pulled up. You can assume that thing visually, that P is the force that is acting along the axis of that cylinder. So then the fiber will be carrying a load of PF and the matrix will be carrying the load of PM all these F and M all are in subscript actually, and you can know from the symbols which are given. So this then PF plus PM will be equal to P, that is the total load acting. The condition for perfect adhesion between the fiber and matrix is that both will extend by the same amount, so that there is no relative displacement between the fiber and matrix. So we are again assuming or taking this thing that the extension of the fiber and the matrix will be same, so that there is no relative displacement between them. So this is a condition, you can say, of the IsoStrain, meaning the strain for both these things will be same. So say if the modulus of elasticity of fiber is EF, whereas F is in subscript, and that of matrix is EM, where M is in subscript, then their individual elongations can be calculated as it is given here. Delta F will be the individual elongation for the fiber, which is given as PF divided by AF into EF. This formula actually comes from the Young's modulus formula itself. You have learnt earlier, that is E is equal to P by A by delta L by L. So since L is 1 here, so delta L is given as delta F here, and P by A you are seeing here PF by AF. Similarly for the matrix, PM by AM. So delta M is equal to PM by AM EM. So this formula is coming from there only, from the elasticity property. Also we know that delta F is equal to delta M, as mentioned earlier. The strain for both of them has to be equal to avoid relative displacement. So if the composite is regarded as a single body, then it is subjected to a force P, and its cross-sectional area is A, total area will be AF plus AM, and its modulus of elasticity is E. Then what will be the elongation? It will be P divided by AF plus AM into E. However, we know that delta is equal to delta F is equal to delta M, meaning the total elongation is equal to the elongation of the fiber is equal to the elongation of the matrix also. So from solving these things, we get the modulus of elasticity equal to EF into VF plus EM into VM, where VF is the volume of the fiber and VM is the volume of the matrix, and it is given as you can see VM by V, total V volume, is equal to AM by AM plus AF, that is the VM, and VF is given by AF divided by AM plus AF, or we can say VF by total V, that is the volume of the composite. So it can be noted from these equations that with decreasing volume fraction of weaker matrix, the modulus of elasticity of composite increases. And naturally the cost of the composite will approach that of the fibers, as its volume fraction will also increase with decreasing fraction of matrix. But this analysis indicates that in a composite a desired property can be produced, and this convenience is an added advantage. According to the volume fraction of the matrix or the fiber, we can have different kinds of properties, so this is an advantage. It may also be noted from the condition of load sharing between the fiber and matrix. Then we can say that sigma C, that is the stress on the composite, into the AF plus AM, that is the cross-sectional area of the matrix and the fiber, is equal to sigma F into AF. Sigma F is for the stress handled by the fiber plus sigma M AM, and sigma M is the stress handled by the matrix. So this relation will hold true. And area of cross section of composite, total composite, is given as AF plus AM, we know that thing, and volume fraction is given by, for the fiber one is given by AF by AM plus AF, and for the matrix AM by AM plus AF. So then we can also write sigma C is equal to sigma F into VF, because AF and VF are equal because the length was unity as taken earlier, plus sigma M into Vm. So sigma C is equal to sigma F into VF plus sigma M into Vm, and this equation can help us in calculating the permissible stress in the composite. So these equations are for knowing the permissible stress in the composite. The earlier one was for the determining the modulus of elasticity of the composite. So certain assumptions were taken for deriving these equations. The first one was that the load on the composite is applied along the direction of the fibers. Because this thing is there, these are very directional things, so if suppose it was applied in the perpendicular direction, then it's a completely different thing, then these equations will not hold. Then the second assumption is that bond between the fibers and matrix is perfect and no slip occurs nor any fiber is broken. So as said earlier, even the strain was taken similar to avoid any kind of relative displacement between the matrix and the fiber, meaning they are moving as one thing only, it's a whole body. The situation under which strains in composite fibers and matrix have been assumed to be same is called IsoStrain, as told earlier to you. So what is the directional strength we were talking about? The modulus of elasticity as well as the stress carrying capacity of a composite is drastically reduced if load is applied in a direction perpendicular to length of fiber. That's what I told you earlier, that if the load is in the direction perpendicular to length of fiber, then it's very weak, it doesn't have strength in that direction. To obtain strength in the two perpendicular directions, fibers may be placed in the matrix along the two perpendicular directions. So fiber may be placed like this, one in the horizontal and one in the vertical. Then both the directions will be having this fibers, and it will be having greater strength in both the directions. But calculation of both modulus and stress in the composite in this case will not be so simple. Since fibers are in both directions, then we have to take into account both directions in the equations, and the calculations become more complex. After the isostrain condition, there is the isostress condition also. In that case, what happens, we are seeing here, the isostrain was type of calculation is applicable to the composite made of layers such as shown in the figure A. So the figure A here is the isostrain type, where you can see the load is acting on the this top face. So it is like all the layers of the fiber, they are all having same strain. Now you see the figure number B. What is happening here? The load is acting in a different direction, meaning it is acting on the side face of the cube, not on the top face. In this case, each layer having same of area of cross section. You can see all layers will have same area of cross section and they will be subjected to same stress. So this is the isostress condition. So total deformation in the composite will now be given as the sum of deformations in the fiber and the matrix. Earlier delta was same for both the matrix and the fiber, but here it is different. So now it will be given as delta C will be given as delta F plus delta M, meaning the strain of the composite is equal to the sum of the strain of the fiber plus the matrix. If the sum of the thickness of fiber layers is LF and that of the matrix is LM, where F and M both are in the subscript, then thickness of the composite in the direction of force P is given as LC is equal to LF plus LM. This is very simple, total length. And from the given equations, what we get then? Sigma upon E, that means stress by Young's modulus. What it gives, we have learnt earlier, stress upon strain is equal to E, so stress upon E will be equal to strain. So that is equivalent to LF plus LM, and it can be represented by sigma by EF into LF plus sigma by EM into LM. Multiplying by A, what we will get? If that equation, previous equation, is multiplied by A, then we get A into LF plus LM by E is equal to LFA by EF plus LMA by EM. And from these arranging these equations, we get 1 by E is equal to LFA by A into LF plus LM into 1 by EF plus LMA in the numerator divided by A into LF plus LM into EM into 1 by EM. So we have separated the things 1 by EF and 1 by EM, and we get the coefficients of that. So we see here that coefficients of 1 by EF and 1 by EM are nothing but VF and VM, meaning the volume ratio of the fiber and the matrix. Earlier we saw this formula, because you can see that this LF by LF plus LM term is coming. So it is similar to that AF by AF plus AM, and we have the A term also, the cross section. So it is nothing but the volume, LF into A. And further we get 1 by E is equal to VF by EF by plus VM by EM. After solving those equations, and we get the Young's modulus in this case, which is given as EF into EM by VF into EM plus VM into EF. So this is the Young's modulus in case of the isostress condition. So here is a figure also which gives us the ratio of modulus of elasticity under the isostrain and isostress conditions. So this graph is between the VF volume fraction of the fiber and between E strain upon E stress. So you can see here that with the increase in the volume fraction of the fiber, in the beginning the curve is going up to a certain level of volume fiber ratio of 0.5 around. It reaches a maximum and then it goes down when the volume fraction is further increased. That means the Young's modulus in the strain condition is increasing with respect to the stress condition up to a certain level of VF, and then it is further going down. So this is a table which gives us the ratio of the isostrain and the isostress Young's modulus. So from the above table it is seen that the highest value of modulus of elasticity under the isostress condition is much small. Why? You can see because E strain upon E stress, you can see the values 18.8, 32.7, all these are quite high values. That means the thing in the denominator is lesser, that is E stress is lesser. And what is the reason for that? Why it is happening in the isostress condition that the E is less? Because fibers do not resist stress perpendicular to the length. So that is the thing. The load I had shown you earlier in the figure, in the case of the isostrain, it was acting in a different direction, whereas in the case of isostress it was acting perpendicular to the direction of the isostrain. So that's why the Young's modulus in the case of isostress is lesser, because the fibers cannot resist this type of load. So what is the solution then? Then the solution is that fibers will be provided in two perpendicular directions as told earlier to you, and the nets, so nets will be formed. So nets of fibers these nets are commonly used as reinforcing elements unless the design conditions require the part to carry only uniaxial load. Suppose the design has to be such that we want load only in one direction, then we don't use these things, otherwise the nets of fibers will be used. And it may also be noted that maximum stress that can be carried by a composite under isostress condition is determined by the lowest of strength of fiber and matrix, since the stress is to be same in matrix and fibers. Obvious it is, because we have to keep the stress same both in the matrix and fiber. So whichever one, whether it be the matrix or the fiber, whichever is carrying the lesser load or it can carry lesser load, the value that of the load will be taking as the stress, because the higher one we cannot take, because the other one will fail if we take the higher value. And even if modulus of elasticity of composite is higher than that of the matrix in isostress condition, it is not of any use, like I told you, because the matrix can carry only lesser load, so it will yield or begin to deform plastically at much lower stress value. So after discussing this thing, there may be a condition where fibers may be broken. So we will discuss this condition now. In isostrain analysis, we will see it was assumed that all fibers participated equally in carrying the load. However, what happens that some fibers may be broken inside, in which case these fibers will not be able to carry any kind of load or force. Then the area of the matrix sustaining this force remains the same, but that of the fibers changes. So there are two things, matrix and the fiber. An area of the matrix remains same, whereas the fiber area changes because some of the fibers are broken. Thus the proportionate contribution of the matrix in load carrying capacity of the composite increases. Obviously, because fiber is not able to take that much load, so proportion of load on matrix will increase. and it is not difficult to conclude that the highest fraction of fiber that can be tolerated to have broken in composite will bring matrix under its permissible stress. So then the load is increasing on the matrix, so it may come up to the level of its permissible stress. If the fraction of broken fibers exceeds this value, then the matrix will be subject to stress higher than its capacity, and definitely it will fail and the whole composite will fail. So here is the figure also for the broken fibers. You can see it is quite clear that some fibers, 2 or 3, it is shown in the figure, that are broken in the middle. So now we will derive certain number of expressions for this, taking these things into consideration. First of all, we assume that the composite in the figure was made with volume fractions Vf and Vm as discussed earlier. For fiber it is Vf, and for the matrix it is Vm, and the sum of these volumes Vf plus Vm is equal to 1. So this is one assumption. And then we will suppose that a fraction x of the fiber is broken, so that the volume fraction of the fiber changes from Vf to how much? Since x is gone, Vf minus x, and that of the matrix will become how much? 1 minus Vm, since 1 was the total, so 1 minus Vf plus x will be the total volume of the matrix, because we saw earlier Vf plus Vm is 1, so Vm will be 1 minus Vf, and since x is gone from Vf, so it will add up in the matrix section, so it will be 1 minus Vf plus x. The breaking of fibers decreases the area of the fiber but does not increase the area of the matrix. So what is happening? The matrix area remains as such, but the fiber area decreases. Hence the gross area of cross section of the composite decreases, because one is decreasing and the other remains same, so total it is decreasing. So area of cross section of composite decreases and area comes in the denominator, so it will now be 1 minus x of the original area. Thus the stress in the composite will increase, because area is in the denominator, force is in the numerator. So stress is force upon area, so we see that the stress is increasing. Now let it be that sigma c dash will represent the stress in the composite, sigma m dash will represent the stress in the matrix, and sigma f dash will represent the stress in the fiber. So from there we get what? Sigma c dash into 1 minus x, meaning 1 minus x is the volume fraction of the composite, is equal to sigma m dash into 1 minus Vf plus x. We have calculated this thing. For the matrix it is 1 minus Vf plus x, and plus sigma f dash into Vf minus x, because x has gone from the fibers, so it is Vf minus x. So this expression comes in. And rearranging this, we get sigma c dash plus sigma m dash minus sigma f dash into x is equal to sigma c dash minus sigma m dash into 1 minus Vf plus sigma f dash into Vf. And finally we get the fraction x is equal to sigma c dash minus sigma m dash plus sigma m dash minus sigma f dash into Vf whole divided by sigma c dash plus sigma m dash minus sigma f dash. To maintain IsoStrain, we know this is IsoStrain condition, so delta will remain same, so sigma f dash by Ef is equal to sigma m dash by Em. Then putting this into the expression of x, we get finally x as sigma c dash minus sigma m dash plus sigma m dash into 1 minus Ef by Em bracket close into Vf whole divided by sigma c dash plus sigma m dash bracket open 1 minus Ef by Em bracket closed. So this is the final expression for x. So in this session we discussed about the composites, what are the composites, and we discussed how they are formed. Two types of materials are brought together, they don't react with each other, they don't react chemically, so this forms the composite. And further we discussed about how composite is composed of the matrix and the fibers, so different types of fibers also, glass fiber and carbon fibers. And further we discussed about the Young's modulus of this composite material in the IsoStrain and the isostress condition. So these things we discussed, and finally we discussed about the broken fibers also. Suppose there are certain number of broken fibers, so how much stress that composite can take, and what can be the level of that fraction of the broken fibers so that the composite doesn't fail. So further things will be discussed in the next session. Thank you very much.